So I'm supposed to tell you a little bit about quantum transport. And of course, this is a vast subject. So as you will see, I will focus on one quantum transport in particular. And so what is the notion of transport? So in condensed matter, since I come from condensed matter, this is literally the routine probe. When you have a new material, the first thing you do, poof, you measure its resistivity, and that allows you to get a first idea of what the material is doing. So this is typically something like this, where you get a battery, and then you have the system of interest that you're trying to understand, and you pass a current. So theoretically, actually, this is a very complicated thing, because that's a completely out of equilibrium situation. You're not probing your system in equilibrium here, but you pass, it might be a steady state current, if the battery is good at least, but it's definitely out of equilibrium. So there is an enormous amount of theoretical challenge into finding good techniques to describe this situation. And the typical situation that corresponds to transport is what I drawn here, where you get one reservoir, the system of interest, and the second reservoir. And usually you put an imbalance in chemical potential, in temperature, in spin, in whatever, and measure the corresponding transport coefficient. Sometimes, actually, one of the reservoir is the system that you want to study. This is the case for scanning tunneling microscope, where you use one of the reservoirs is a stupid metal, let's say, and the second reservoir is the very fancy compound that you're trying to understand, and there is nothing in between, but you try to pass a current between these two systems, and by measuring the current as a function of the voltage, you try to extract interesting properties of the system. The way to cheat the out of equilibrium difficulty is, of course, very often, but sometimes we simply cannot do it, to focus on linear response, where you say that the current is proportional to the voltage, and this allows you to define something which is called a conductance or a resistance, depending on the case. So dealing with a full transport in half an hour is impossible. So first, before I go to this, why transport? As I said, it gives access to physics of complicated material. Very often when you want to use a material, it's for its transport properties. Superconductor, you want it because it transports current without losses. So this is one of the most important quantity that you want to have. And as I said, on the theory level, we desperately need a new technique to study this. I'll try to illustrate it by the case that I will show you in great details. And of course, since we are at a conference on cold fermions or hot fermions, I don't know, we can say that this is a fantastic situation to deal with the study of transport a priori, because this cold atom allows to implement a very controlled model with a very large degree of control. So this is what I won't tell you about, and I'm very sorry not to be able to tell you about these things, but don't hesitate to ask me if you have any questions. So these are works that we did mostly with Anne-Maria Visuri and Corinna Collat in collaboration with a group of Tillman Esslinger. Typically transport between two reservoirs through chains which could have loss of particles, which gives a very interesting transport, which is known as a quantum Zeno effect. So this is something interesting. Or transport between two superconducting reservoirs through what is known as a quantum dot or a quantum point contact, which shows a mechanism known as multiple Andreev reflections. All this, we worked on it, but I won't have time to tell you about it. A more recent and more theoretical proposal done with Tony Gin, João Ferreira, and Michele Filippone, which is in want of an implementation. So if people feel brave, don't hesitate. We have again the two reservoirs, we have the chain, and on each side of the chain, one put a noise which varies both in space and in time. And this leads to very interesting effect. This leads to diffusion, which in 1D is not easy, but also to, again, a certain number of out-of-equilibrium phenomena. So I won't tell you about this, and I want to focus on one particular transport quantity, which is the Hall effect. And why I do this, first because, again, time is limited and one has to make choice, but also because I think the Hall effect illustrates very well how the combination of techniques that I think the panel mentioned yesterday can allow to obtain the interesting results that we would not have obtained otherwise. And it's also something that can be efficiently quantum simulated in cold atoms. So here are the people who did the work. I won't read all the names, but you recognize some of them who were here, in particular Uli. So this is the work on the Hall effect on the theory side. We had the great fortune to be able to collaborate with a group of Leo Falani in Florence, and Tianwei Zhu is the person who was really, heads-on with the experiment, and I'll show you the implementation that this experiment allowed to do. And finally, if time permits, I will mention some more recent results we obtained with Edmond Rignac, Roberta Citro, and Catalina Lati. The paper with Roberta and Edmond has been put on archive yesterday, essentially, so this is really new results, where we could compute analytically some of the quantities that I mentioned to you. So what is the Hall effect? So let me go back to Hall effect 101. You take a piece of junk here, you contact it, you pass a current in this direction by putting a voltage, for example, and then you measure the tension which develops perpendicularly to the current. Of course, there is a magnetic field which is creating a Lorentz force deviating the particles. So they go and they accumulate on this side and they create the voltage difference that appears in this system. And now, if you have non-interacting particles, you all did this calculation at one time in your life, you equilibrate the Lorentz force with the electric force, and you find that the Hall resistance, which is the Hall voltage divided by the current, and divided by the magnetic field. By the way, I won't talk at all of necessarily large magnetic field. I'm not going necessarily to the integer quantum Hall effect or fractional quantum Hall effect limit where B is very large. We'll talk about this, but here I want even to stay in the limit of small fields, what people sometimes call very improperly the classical Hall effect, which is everything but classical. So the most well-known urban legend is that this quantity is measuring 1/n, where n is the number of carriers. And already we know that for non-interacting particles, this is wrong. If your Fermi surface has some curvature and so on, there is a very famous formula, which is the Thouless-Komoto formula, which relates the Hall effect to topological invariance of the Fermi surface, and so on and so on. But this is for non-interacting particles, and of course, if the fields become large, you get the integer quantum Hall effect, and so on and so forth. But essentially, with interaction, what the Hall effect is measuring in an interacting quantum problem is largely an open question. And this is something where there are conferences, in HITC in particular, where there is blood on the wall when people discuss what is the interpretation of the Hall effect, and I will certainly not do this. Let me show you by showing one experiment in condensed matter, which is an experiment done with organic superconductors, which are good realization of weakly coupled fermionic chains here, where the particle mostly move in this direction but can tunnel in the perpendicular direction. The magnetic field is put perpendicular to the planes, let's say, where these chains live, and the current is passed here, and the Hall effect is measured in the perpendicular direction. And just to show you that even at the experimental level, there is debate. Here is one experiment which was done in Orsay, where you see a considerable temperature dependence of the Hall effect between 300 and 150 Kelvin. And here is the same experiment done in Lausanne, which shows physics is not invariant by translation in space, because this time you see a flat temperature dependence in the same regime of temperature. Why? Nobody knows. Note the date of the experiments. Nobody was brave enough to provide a third set of data to show which experiment was wrong, or if both experiments were wrong. So just to say that this is a complicated situation, and ideally that's the thing one would love to solve. Many couple, for example, chains, a magnetic field perpendicular to it, and measure of the transverse Hall effect. And with Antoine, 1 century ago, we committed some paper dealing with this issue. This is a complicated problem. It's very hard to deal with the calculations. So here I will sort of be less ambitious, and instead of having an infinite number of 1D chains, I will do 2. So this is the ladder. So this is trying to study the Hall effect in the ladder geometry. So you have 2 chains of fermions or bosons. I guess I'm still allowed to pronounce the word bosons in this seminar. The particle can move along the chains. You can have a lattice, or it can be continuum. It doesn't matter. But the point is the particle can tunnel from one chain to the next. And when they tunnel, there is a gauge field, which represents your magnetic field. And they accumulate some phase when they go through. And of course, what you want to do is to pass a current along the chains and measure, in principle, the voltage or the imbalance that will be created by this magnetic field. So this is nicer. It has, you can control the things with a number of legs. The systems are clean. You never know for the compound. You will look whether disorder plays or doesn't play a role. The interactions here are the unique source of scattering. And there are experiments, as I will show you, where you can measure the whole polarization and the whole voltage. So this is something that got implemented a long time ago in the cold atom community. Let me show you some experiments. So a pioneering experiment in the group of Leo Falani, where they use what is known as synthetic dimension. So there is no really several chains, but this is several states of an internal degree of freedom of the atoms. And you do transitions between this internal degree of freedom, where you choose carefully the phase when you do the transition so that it corresponds to a uniform magnetic field. And you can measure separately the population of each one of these species, so you know how many atoms you have on this chain, quote, on this chain and on this chain. Physically, it's a single chain. So you can pass a current by giving a kick to the system, and therefore you can measure the Hall effect. And in this 2015 paper, this is something that was done. Very similar experiments done in the group of Jan Spielmann in Maryland at the time. There are very similar experiments done in the group of Jean Dalibard and Sylvain Natsimbene in Collège de France, where I forgot 11 or 13 chains are probed. All this was done with ridiculously weak interactions. So this is essentially one particle physics. So now, what would happen with interactions? So this is something we did with Sebastian Grechner and Michele Filippon. At the time, they were postdoc in my group. And the way we attack this problem is essentially numerical. We didn't know how to do it analytically initially, so we decided to do DMRG calculation using the fantastic power of DMRG. Thanks, Steve. And the way we wanted to do it is, of course, ideally to put a current, so ring, but Giamarchi is better in a box, so this was not so convenient. And experiments also very difficult to get a ring. So finally, we opted to say, let's do like the experiment do. We take a box and we give a kick to the system. And this will create a current that will go in this direction. And then we will measure the population difference from the top chain to the bottom chain. Actually, what you see here on the plots, I don't know if Steve would approve the drawing or not, but what you see as a size of the dot is the population. So you notice this is the result of the DMRG. You see that there are more atoms on the top chain than on the bottom chain, and the arrows denote the current. So you see that the current is not flowing uniformly, but you can still determine the total current. Okay. In practice, this looks like this, and there we are incredibly lucky. Why? Because this is the time, this is the current. You see it's strongly time dependent. And these are times short enough that the current doesn't go crashing at the edge and things like this. This is the polarization of the system. But you see that the ratio of the two, which is defining the whole imbalance, let's say, is equilibrating very, very fast to a plateau. And we can extract from this out of equilibrium experiment something that corresponds to a steady state value. We can check for non-interacting particle that this is the right steady state value. But at that stage, we had no more than the non-interacting particle. But we notice something on the numerics, which is if you change the density, there is a region where at some point, the whole imbalance sort of saturates, become flat. This is for 2 chains, 3 chains. Let's forget 3 chains. Saturates. This we could also compute analytically by saying if I have tunneling, I have several bands, I'll split the system. And if the tunneling is very large between the chains, so if T perp is much larger than T parallel, we can separate the bands and do a kind of perturbation in the transition to these upper bands. And what you find is a big surprise that you have an interacting system, you have all the complications in the world, and in this regime, the whole resistance gets back to 1/n, to the naive classical value. So we had this, I would say, numerical and semi-analytical, because this was done for non-interacting particles, evidence that there was a universal value of the behavior of the whole resistance, that if the tunneling became large enough or the interaction became large enough, the whole resistance was going back to its classical value, 1/n. In order to decide whether this was a robust procedure, we teamed up with the group of Uli Scholvöck, and Max Buser is the person who did the brunt of the calculations, to try to compare our kick procedure with the one where we would put a flux here and pass a steady state persistent current and then measure a steady state whole imbalance. And we also found a way not to deal with the whole imbalance, which is the population imbalance, but to deal with the whole voltage, which is that you change the chemical potential so that the imbalance becomes 0. And that's what corresponds to the normal Hall voltage. So here is just to, in short, this is the same result, whether you use the kick or whether you use this procedure. Let me show it to you. Here is the kick procedure, polarization, current, oscillations, saturation. The green line is the simulation with a periodic boundary condition. The red dots are the value that you extract from this plateau. You see that for the whole imbalance and for the whole voltage, the two are agreeing perfectly. So we are very confident that we are not fooling ourselves by doing this. Why worry about the whole voltage? Okay, first, these are two quantities. If you want to compare with literature in condensed matter, you will probably prefer to look at the whole voltage, because this is what is usually reported. But also, let me give the example of the two-leg ladder of bosons, which is a problem we studied a long time ago with Edmond Aurignac At the time, there was no, let's say, cold atom turned towards condensed matter. So we had in mind Josephson junction arrays. But this is a nice problem that now has been simulated in the group of Monika Edelsberger and Emmanuel Bloch. And they essentially confirmed that what we computed at the time is perfectly correct. And let me just tell you what happens. If you don't pass a current, just put a magnetic field. At first, when the field is weak, you get currents which are only circulating at the edge. This is like a Meissner phase, where you would have in a type 2 superconductor currents which are only circulating at the periphery. And then when you exceed a certain threshold of field, vortices start to enter. And you have here, you see the vortices, the red part, are parts where there are loops of current here that thread the ladder. So you have you have a quantum phase transition between a Meissner phase and a vortex phase at large field. And you can study this, which is what we did in this paper. And this was observed in this paper. But if you look at the Hall effect, you would see that there is a singularity in the Hall effect when you start approaching the vortex phase. And therefore, the Hall effect is a probe of this quantum phase transition. Now, if you look at the Hall imbalance, the curve don't scale very well. If you have different legs, different things, the curve don't fall on the top of each other. If you look at the Hall voltage, all these curves fall on the top of each other. So the Hall voltage seems to be more robust than the Hall imbalance itself. In any case, it's good to have both quantities. Okay, so that's the story. That's where we are, or where we were with this. And there was this sort of remarkable observation or question that the Hall effect could go to 1 over n in case the interaction was large enough or the tunneling between the chain was large enough. So can one test this in a quantum simulation? And the answer is yes. And as I said, this was done by the group of Leo Falani and Tianwei Zhu. And on the theory side, Michele Filippon and Cécile Repellin were doing the brunt of the theoretical work. And essentially, let me show you the simulation. So this is the same system than I showed you before, the 2015 experiment, except this time they control the interactions, essentially by squeezing the system. And so this is the artistic view of the ladder, where you have the gauge field, the artificial gauge field, which corresponds to a magnetic field. Then they give a kick to the system. The kick is giving Lorentz force, and the Lorentz force is accumulating particle here. So this is the artistic view. What is below is not the artistic view. This is data. So you see that the momentum distribution shows that there is a difference between plus k longitudinal and minus k longitudinal. So this corresponds to the kick. And this is images of the polarization of the, let's say, difference of population between this side and this side, which corresponds to the two quantum number, -1/2 and -5/2. Now, again, one has something where if I look at the experiment as a function of time, I get for the current something like this. Then things get south, if I could say. So we should concentrate on this part. The polarization is giving curve like this. The shady curves here are the kind of theoretical expectation, taking into account the average over all the tubes with different densities and so on and so forth. Again, get rid of the trap, get rid of the trap, and get rid of the trap. It would simplify life very much here. Okay. Again, the ratio here goes to, it's less nice than if we do the simulation, but it still go to something which is a reasonable universal value. And lo and behold, when you plot the data point, you see two things. You see that as a function of the perpendicular tunneling, the data seems to converge reasonably to the value that you cannot cheat with this value. It's 1 over n, so you know what it should be. And same thing when you have large interaction, the data seems to converge reasonably to, again, 1 over n. You see also that if the interaction is not large enough, the value of the Hall effect is something, which is not at all a simple number, which is not 1 over n, and which depends on the interaction and on the characteristics of the system. You see also another thing, which is this curve is again the theoretical expectation. Unfortunately, the experiment is done at finite temperature, not negligible temperature. The simulation we could do was only at t equals 0. We tried to cheat a little bit and reintroduce by hand the temperature. So here it has absolutely no importance because this is a plateau. So, you know, it doesn't matter what you do, you should find this plateau. But we were trying to see if we could also reproduce this part, and the answer is a flat no. With the bad calculation we, quote, did at t equals 0 and trying to do a little bit of mean field to put the finite temperature, we are not able. So what is needed now is a real calculation at finite temperature, averaging over the trap at finite temperature, and then maybe this will go through the data point for this part. This part is okay, but this part, I don't know, but this is a case where the quantum simulator is in advance, I would say, to the capacity. So I think this would be very interesting to have these results at finite temperature, either by DMRG or by quantum Monte Carlo, at least for the steady state solution, which I think can be done also by quantum Monte Carlo, and answer the question on whether this part poses other problems or whether then this is fitting reasonably with the data. But the plateau, the universal value 1 over n, is definitely in agreement with the theoretical prediction. So let me just finish. I think I have, 10 more minutes or 5? Yeah, okay. So recently, very recently, together with Roberta Citro and Edmond Rignac, we were able, in the opposite limit, the limit of small t perp, to find an analytical derivation of this behavior. So I won't go into the calculation detail, but this is using field theory, so-called bosonization technique. And so this is the same ladder. This is just to say you put a voltage to cancel the imbalance. So again, whole imbalance or all voltage. So what do you do? If you have bosons, let me take bosons. We can also do fermions, but bosons are simple. There is a representation of the boson operator in terms of collective coordinate. One of these coordinates is the phase of the boson wave function, and the other is a collective coordinate connected to the fluctuations of the density. And essentially, the density is rho 0. There is a rho 0 missing here, minus 1 over pi, the gradient of another phase. And because phase and fluctuations of density are conjugate, this phi is conjugate to theta, or rather to the gradient of theta. So this is a very well-known technique used in 1D. And so normally, everybody would write the Hamiltonian using this mapping for one chain, for two chains, write the tunneling between the chains, which has a very simple form. It's like two bunch of harmonic oscillators coupled by a cosine term. And then if you do this and you compute the whole effect, you find 0. You find 0 because this model has a hidden particle-hole symmetry. You linearize completely the dispersion relation, and therefore you implement in this model a particle-hole symmetry that doesn't exist in the original model. And to correct this, you have to include very ugly terms that Haldane explained to us how to include. It's cubic terms and so on. But you see that now I have a theory that I don't know exactly what to do. And that was a big problem in the, I would say, prehistorical calculation that we were trying to do with Antoine with the many chains, because this term had to be treated in kind of perturbation, but you also need to do something with the tunneling and blah, blah, blah. So here, it's simple enough that one can deal with this term. And the idea is the following. You know that the whole resistance will be 0 if this term is 0. So the whole resistance has to start at least at first order in this term, which means you can write an horrible average, but this average can be taken without this term in the Hamiltonian. So to cut a long story short, let me show you the formula. The whole polarization can be easily connected to the current longitudinal current, which in general we don't know how to compute, but we don't care because we divide by this. And then the fluctuation of the anti-symmetric component of the charge density. And when you do this using, again, Latinger liquid theory, you have an explicit formula of the whole polarization normalized by the field and normalized by the current as a function of the so-called Latinger parameters of the problem. And again, this will give you a polarization that starts to increase with the flux and then decrease with the flux if you don't do the approximation of small flux. But where it becomes really interesting is when you try to address the whole voltage. So we can do the same calculation with a whole voltage, take a voltage to cancel the population imbalance, blah, blah. You turn the crank. And what you find is this formula, that the whole resistance is the derivative with respect to the density of the log of a certain product of this so-called Latinger parameter. But this product is what is known as the charge stiffness. That's the peak of the Drude peak of the weight of the Drude peak in the conductivity of the system without a flux. Or, if you prefer, that's the response to a twist in boundary condition. Some people would call it the winding number in Monte Carlo or the charge stiffness. And this is a kind of remarkable formula because it tells you that one transport coefficient, which is the whole resistance, is nothing but the derivative with respect to the density of the log of another, I don't know if I should call it transport coefficient, but thermodynamic coefficient, which tell you how your system responds to a twist in boundary condition. You get, yep.
Sorry, this is going
I
back
think you
a little
should
bit.
Use your mic. But
It's on, believe
Sorry.
it or not. It's to these cubic terms. So these are irrelevant terms in
Yes.
the bosonization, but they need to be there for the Hall response. Is the Hall response still universal? You know, does this have implications?
I'm going too far here. So you're totally right. These terms are irrelevant. They are higher power, so that's usually why they are removed. But here it makes the difference between 0 and something. And you can check for free fermions that indeed the whole resistance is proportional to the curvature. So the question you're asking is a very good question, is this formula that I showed you really correct? Or is it just correct to first order in the band curvature? We only derived it to first order in the band curvature. Now, I will show you one or two tests that we did, which seems to imply that the formula is correct, and there should be a more intelligent way to derive it. But whether it's true or not, so again, people who know how to compute and simulate, go for it, because this is something, we are doing it also a little bit with bosonic ladders, trying to compute separately the stiffness and trying to compute separately the whole resistance. But that's clearly an interesting thing. Or how is this formula staying if you have 2, 3, 4 chains? I don't know. But certainly for me, sometimes when people see this formula, they tell you, oh, that's the Streda formula, which there is a formula for the integer quantum Hall effect, which is known as the Streda formula, which gives the quantum Hall in terms of, indeed, derivative with respect to the density. But that's a completely different range of applicability. You need the bulk to be gapped for that. So here, a priori, at small b, there is no gap, there is no bulk. So I don't know. So, but that's a very good question, what you ask. I cannot prove to you that this formula is correct to all orders, but it's certainly derived to first order in perturbation theory. In the curvature, all interactions effects are taken into account non-perturbatively. Okay, for a Galilean invariant system, we know what this is. There is a conservation law that says that this is rho 0 over m. And when you do this, you find the 1 over n value that we derived or we obtained from the numerics in a different limit. But you at least recover this 1 over n for Galilean system. So this seems to be consistent with what we get. You also get something for free, that if you have an insulating phase, the stiffness will go to 0. Will go to 0 as density minus critical density. And when you differentiate the log, you will get a singularity in the whole resistance. So it immediately tells you that if you have a whatever superfluid insulator transition, your Hall resistance will diverge on both sides with a sign that will correspond to the approach to the transition, whether it's band transition or whether it's MOT or other correlated system. So this has a lot of appeal as a formula. Just to flash one last result, Antoine. I mean,
yeah, can you go back to the previous slide? So gamma has disappeared from that formula.
yes. So the reason it has disappeared is because for the bosonic ladder, there is an expression of gamma as a function of the Luttinger parameters themselves. It's quite a remarkable expression. It was derived in, not by us, but it was derived around the Tonks limit. So we use this expression to inject in the other formula, and that's how this derivative of UK and whatever.
It's an additional condition that relates the leading irrelevant operator or whatever.
For bosons.
Yeah, I know.
For bosons.
It's not general.
It's not general. Yeah.
So in general, the formula you derive from RH will contain gamma.
Well, it contains the band curvature alpha, let's say, the other one, this one, yes, the other one. We did, I don't show it, but it's in the paper, we did the same derivation for fermions, of course. So this works also for fermions. And indeed there, you know from the dispersion relation of the system what is the coefficient alpha. For bosons, you could say what is the dispersion for a k-square boson, where is the Fermi level and whatever. So this is where these formulas are taking place. But again, I'm aware that this poses more questions than I can give you answer for, but just to tell you that separately for fermions, for bosons, we consistently end up on this formula. Just to flash one last result with Catalina Latti, who is doing a postdoc in my group at the moment and is a wizard with Giamarchi. We started to look at a triangular ladder to see the effect of frustration on this. So the triangular ladder has a phase diagram which is complicated enough. I won't discuss this, but let me just show you. So it has the Meissner phase, the vortex phase. It has something which is a biased chiral superfluid phase where there is a spontaneous imbalance of population without current, which is created, so a breakdown of Z2 symmetry, which is created there. And let me superimpose on this phase diagram the Hall effect. And you see indeed that also there, the Hall effect has singularities that track very well the quantum phase transition, for example, when you go from the Meissner to the vortex phase. So this is an efficient probe to tell you where your quantum phase transition will take place in the system, and same thing for other boundaries that I don't want to discuss here. Okay, my time is up. So I think there are remarkable properties of the Hall effect for interacting quantum systems. It's a nightmare for theorists, but it's a fantastic field to play with, and you don't need to go to quantized value of the Hall effect for that. We found this remarkable universal regime 1 over n for large tunneling or large interaction for the ladder systems. And of course, this prompts for a lot of questions. This was confirmed for the 2-leg ladder system in experiments. But of course, we would like to know what happens if we increase the number of legs and so on and so forth. What happens if we go to finite temperature? We supplemented this derivation by an analytic expression which relates the Hall effect to the charge stiffness, which is again a kind of magical thing. Frustrated systems also offer their share of question, but the Hall effect is clearly also a very good probe to tell you where the quantum phase transitions are in this system. And finally, if one wants to go to simulating many chains, which would be at the end, the goal is to really do a 2-dimensional or 3-dimensional system. Again, it would be much better if we can get a homogeneous system to do this. So get rid of the tram. And thank you for your attention.
So you had this formula for the Hall resistance where the sign changed across the MOT. So should I interpret this as sort of the particles are carrying the current on one side and then the holes carry it on the other?
That's usually what people do. And certainly if it's a band insulator, this is a very, but people also discuss similar classification around the Mott transition and whatever. I'm just saying here it comes out very naturally out of this formula. And indeed, it seems to suggest that you would like to call particle and holes the two sides. And that's fine.
So this beautiful formula reminds me of something. So several years ago, Shastri looked at the high frequency limit.
Yes.
I'm sure you know these papers.
I know
right?
these papers.
And indeed, he derived a very similar looking formula for the thermopower, which relates the thermopower to the derivative with respect to density of the entropy. He called this the Kelvin formula, but it should be called the Shastri formula, really.
Yes.
And it turns out this is a very good approximation in many cases to the actual thermopower in the correct limit. So did you think of the high frequency limit?
Not at the moment, but that's something that...
'Cause I would bet that this comes out.
Yeah, there is also a connection for the formula, which is known as the Mott formula for the Nernst effect. I just saying that we are still trying to digest the I would say implications or not of this type of formula, but indeed trying to go to the large frequency. We had a couple of years ago on the triangular system a paper with Gladys Leon and Andy Millis on the high frequency Hall effect. So these are things that we should worry about. But as I said, this paper is on archive 2 days ago.
Nice talk, thank you. You had one plot where I think the DMRG came a bit lower than I think your universal prediction. I was wondering if you understood. Yes, I think it was the next slide with the.
Yes.
And
So-
the experiment even seemed closer to the red curve.
Yeah, so this is the DMRG, but you have to realize that the DMRG for which density? Unfortunately, you get a bunch of tubes, and what is the density you should take, which is important for 1/n. It's not 3/4 or 1/8. So you have to decide whether it's the center tube. So you have to weight the tubes according to their numbers, their distribution, what is the population on the tube. So we tried to do this type of averaging, and that also leads to the various curves that you see here. So I think progress can be done on both fronts, on the DMRG or numerical side, including the finite temperature effect, which is very finite, would be definitely a good thing. Because forget this MFA and whatever, this is just to try to do something. But as you see, it doesn't work very well. And then on the experimental side, of course, I mean, the more homogeneous, the better. And then either there will remain a problem here or not. If this problem is eliminated, all is good. If the problem is still there, okay, then we have something else to understand, but hopefully this would solve this point. Already, the plateau was very kind to us because the plateau at least doesn't crucially depend on you, doesn't crucially depend on T-perp and so on. So it simplifies a certain number of averaging.
Okay, let's thank Thierry.
Thank you.